The systematic steps of actually doing science requires first going out and making some general observation about the natural world, and then going through a set of successive steps to some sort of specific conclusion. And we all know this as the scientific method, which starts with something very general and ends with something very specific. The most general aspect of the scientific method is simply making an observation, going outside and seeing something with your eyeballs about the natural world. What do you actually see in nature? And the reason why observations are great is that they lead to questions. So if you go outside on a given day and you look up and the sky is blue, that's your observation, you might ask, well, why is the sky blue? I know we kind of take that for granted. Why isn't it purple? Why isn't it green? Why isn't it red? Well, I guess it's red sometimes during sunset, but why is that? After we make observations and think of questions, we formulate hypotheses. Now, a hypothesis is one of those loaded words, which again, sometimes the general public and scientists aren't necessarily aligned with. But even scientists don't always agree on a definition for hypothesis because in some fields the definition is so specific, for instance, in statistics. But in a more general sense, a hypothesis is simply a possible explanation for an observation that you have made. So whether it's you in the morning trying to figure out why your car won't start, or a scientist, we formulate hypotheses based upon previous knowledge, inference from a similar situation, or just common sense. Let's go back to the example I alluded to a second ago. You get in your car to come to school in the morning and the engine doesn't start. What now? Well, you need to develop some hypotheses for that observation that the engine doesn't start. Well, where's the first place that you go? For me, it would probably be to check that there's gas in the car, or maybe that the battery's not dead. The thing I'm probably not going to do first is check to make sure that some garden gnome hasn't stolen the engine in the middle of the night, because that just doesn't make a lot of sense. And I've had very similar situations before where the battery was close to dead, and when I tried to start it the next morning, it just didn't work. Now, let's say that you made a hypothesis or developed a hypothesis that there wasn't any gas in the car. And then you go and you check, and lo and behold, the gas tank is full. Do you just say, well, it's not the gas, so I don't know what it is, I guess I'm just going to get rid of the car? No, of course not. You develop several alternative hypotheses, because if the first one isn't supported by data, you can move on to subsequent hypotheses. After you check the gas and you see that it's full, you go and check the battery and see that it's dead. So alternative hypotheses are critical for any part of the scientific method. Now, once you have made an observation, asked a question, and proposed a hypothesis as a possible explanation for that question, you can make some predictions and you can gather data to test those predictions. So again, if it's the battery that's not working in the car, then maybe if I go and get a different battery and try and start the car and it starts, that tells me that, of course, it was the battery. Let's extend this exercise to something else. You go to study late at night and you see that your lamp doesn't work. So your observation is your lamp doesn't work. What is your question? Obviously, why the lamp doesn't work. So there are a number of testable explanations, which include that the lamp is not plugged in, the bulb is burned out, the wiring is faulty. We can develop some predictions and run some tests and collect some data, and these can be really simple. I'm going to look and see that the lamp is plugged in. And if it is plugged in, maybe I'll move it to a different outlet in case the wiring is faulty. And if it's still not working, I'm going to take the bulb out and I'm going to try the bulb in a number of different lamps, and I'm also going to get a nice fresh bulb and I'm going to put it into the lamp and see if it works. So we're testing several different alternate hypotheses and collecting data for each one. What are some untestable hypotheses, some untestable explanations for why the lamp doesn't work? Well, here are some that we came up with. A demon has cursed it. Can't really test that. The flying spaghetti monster hath blocked me. It just wasn't meant to be. My horoscope said I'd have trouble today. Now, just like we talked about before, and in this example as well, this is a process. This isn't some end-all, be-all. And as you are developing predictions and gathering data, you will often refine and alter or expand on your hypotheses. You might also reject those hypotheses. If we're talking about the lamp, and the first thing you think is that maybe the wiring is faulty, and you go and plug another lamp into the same outlet and it turns on, well, then you can reject that hypothesis. Or, maybe if you're working on the light bulb and it doesn't work, and you see that you're using the wrong wattage, then you can alter or expand your hypothesis that the light works, but it's the wrong wattage. So this is a process. This isn't a yes or no black and white equation. And again, the general public sometimes has a problem with this when scientists are communicating and scientific ideas are changing and in flux. Now, more broadly, not just talking about our lamp, but talking about science in general, the end goal of all of this observing and questioning and hypothesis forming and testing is to develop general theories about how the world works. And if there's one word in biology or in science that the general public really gets wrong, it's this one. So let's talk about what a theory is. First off, a theory arises after many alternative hypotheses tend to support the same general conclusion. What is a theory? Well, a scientific theory is a well-substantiated explanation of some aspect of the natural world based on knowledge that has been repeatedly tested and confirmed through observation and experimentation. Let that sink in. It is a well-substantiated explanation of some aspect of the natural or physical world based on knowledge that has been repeatedly tested and confirmed through observation and experimentation. What is a theory not? It's not a hunch. It's not speculation. It is 180 degrees the polar opposite. Why do we aim for theories in science? It's because scientific theories have not only predictive but explanatory power. That is, we can make predictions about how the world works after we have developed general theories. And evolution, as we will see, is no different. Farmers every day use evolution to make predictions about which cows they should mate, which corn seeds they should plant. We use these general theories every single day in our lives, even if we're not always aware of it. Scientific theories are the most reliable, rigorous, and comprehensive form of knowledge that exists. So all of these endeavors of pushing the boundaries of our knowledge is so that we can try and develop some sort of explanatory and predictive ideas about how the universe works. I mean, that is really the goal of science, is a general understanding of how our universe works. So what have we learned today? We've learned that biologists for a long time, and even today, study natural history. And natural history observations are the facts of life. What animals do, what they eat, where they live, who they interact with. Natural history observations also lead to either proximate or ultimate questions. That is, how do certain things function or work, or why have they evolved the way that they have? Evolutionary science in particular helps us to answer why it is that organisms look and behave the way that they do. Evolutionary science, but really all science, is guided by a set of principles. Those are the 4 guiding principles we talked about. New knowledge is gained through the scientific method, and ultimately theories are generated through the scientific method, and they are the most comprehensive form of scientific knowledge that we have. Now let's go back to slide 5, and I asked you, how many beetles do you think there are on Earth? Well, scientists are constantly describing new species. There are about 1.2 million described species of organisms on Earth. There's likely around 8.7 million. That tells you how many haven't been described. Estimates range from about 7.5 to 10 million species that have been described on Earth. Of the 1.2 million that have been described, about 350,000 of them are beetles. 350,000 are beetles. So we're talking like 22% of all life on Earth is a beetle. So that's incredible. That is absolutely incredible. And we'll actually talk about why that is. There is an answer to the question, why are there so many more beetles than other organisms? One famous evolutionary biologist is J.B.S. Haldane. He lived in the 20s and 30s and 40s. And he was at a meeting once where somebody asked him whether or not he believed in God. And he had an ingenious answer, which is one of my favorite quotes of all time. And what he said was, "The Creator, if he exists, has an inordinate fondness for beetles." We will end there, and we will continue on Thursday by talking about Darwin and natural selection. See you then.